The Airbus A380 is a truly amazing feat of engineering. In a purely bums-on-seats configuration, this aircraft can take almost 900 passengers. A typical coach takes about 50 passengers, so the A380 can take approximately 18 coach loads of people. That's a lot of people. The next video clip is from the US Air Force, showing the filling and strapping down of the large bladder tanks used for in-flight refueling of their aircraft. Bear in mind that these 3 tanks are only 9,000 US gallons. This is just under 10% of the fuel needed to fill the A380. Look at the lengths these guys go to and the amount of straps needed to stop this lot sloshing around. Also, this 9,000 gallons takes up a good portion of the aircraft's cargo bay. Where on earth would you fit 10 times this amount on an A380? Is it making sense to you yet? A380 can take 323,525 litres of jet fuel in the wing tanks. That works out at roughly 260 metric tons, or 130 tons of fuel in each wing. I'll let that sink in for a minute because that is very, very heavy. That is the same as 16 red London double-decker buses on each wing. Or to put it another way, a herd of 22 fully grown elephants on each wing. How does that sound to you? Pretty incredible, right? But you can look this information up in the specifications and check it for yourself. It would take 16 of these 20,000 litre trucks to fill the A380. Where does all this fuel go? In the wings, you say? Okay, let's take a look at the wings, and you tell me where you think it all goes. This is the A380 wing. Pretty huge. Let's put a fuel truck next to it. And another. And another. And another. And 4 more. Just for this wing. Another 8 go into the other wing. Can you see what I'm saying? Now let's take a look at the wings on these aircraft. This is the new Dreamliner taking off in a spectacular fashion. Observe the thickness of the wings. How many fuel trucks would fit in those wings? Okay, let's take a look at the fill rate. To fully fill the A380 takes approximately 45 minutes. To fill an Olympic-sized swimming pool takes about 4 days. That is 2.5 million litres of water. The capacity of the A380 is about 8% of the volume. 8% of 96 hours is 7.6 hours. That's a lot longer than 45 minutes. So maybe the filling equipment is much faster for a plane. Let's take a look. This is filling a swimming pool. And this is filling an aircraft. To fill the tanks of an A380 in 45 minutes, you would have to have a pump and a hose that could pump 7,189 litres of fuel per minute. Let's look at something that pumps at a half that speed. Now the plane, now the fire hose. Don't you think that filling that wing with that sort of pressure would just rip a hole right through the top? It's only made of aluminium. So far, we have no room for all of that fuel, an incredible weight of fuel, and a filling procedure that makes no sense whatsoever. Time to take a look at moving around with large bodies of liquid. The size of a large car's petrol tank is about 70 litres. Don't you sometimes wish that your petrol tank was bigger so you wouldn't have to fill up so often? There are reasons why this is so. Number one, the weight would drastically reduce the performance of the car. And number two, the amount of fuel sloshing about in the tank would seriously interfere with the road holding whilst going around corners. This doesn't seem to be the case with aircraft using vast quantities of fuel. Let's take a look at what large bodies of liquid does to road holding. Not a pretty sight. Now let's look at a couple of landings of aircraft and try to imagine hundreds of tons of fuel sloshing about in the wings. I think you might be getting the gist of what I'm trying to say. It is ridiculous to think that these aircraft take off, fly, bank, maneuver and land with large amounts of liquid moving in all directions. Most of us have seen a plane refueling. They connect one or two hoses underneath the wing, connect that to a pump on board a refueling truck, which then pumps the fuel from underground tanks. This takes about 45 minutes for a full load. We never see the amount being pumped because the tanks are not visible.
For real?
Yes.
What are they going to burn?
Nothing. Ultra high pressure compressed air.
Whoa. Just
gas,
air?
Cold gas thrusters.
Now, do you have to have air tanks, or are they just sucking the air out of? Okay.
Yeah, it's an electric pump.
Whoa.
Pump it up to like 10,000 psi.
And how fast are we talking? 0 to 60?
How fast do you want to go?
Welcome back to Malabar. Safety is number one priority. And today we're gonna do a compressed air experiment. All we're gonna do is empty water bottle. Let's get to it. So check it out. It's very easy. Make sure your lid is pretty tight and just start twisting it. Just twist it. Don't worry, it's not gonna explode in your hand. And guess what? We got vacuum in there. But then we're gonna untwist it over here. Check it out. Now we got, I don't know if you see it on camera, but we got smoke bubbles. Alright.
Air?
Cold gas thrusters.
Now, do you have to have air tanks, or are they just sucking the air out of? Okay.
Yeah, it's an electric pump.
Whoa.
Pump it up to like 10,000 psi.
And how fast are we talking? 0 to 60?
How fast do you want to go?
Hyperloop 1 successfully conducts first propulsion test. Hyperloop 1, formerly known as Hyperloop Technologies, has successfully conducted the first open-air test of the Superfast train's propulsion system in North Las Vegas, Nevada. The fully automated Hyperloop is propelled by linear induction motors. The compressor at the front of the pod sucks in air, pulling the pod forward. The compressed air is used in the air bearings underneath to levitate the pod. The fully enclosed tunnel allows the pod to travel as fast as 700 miles in an ultra-low pressure environment and is unaffected by weather conditions. Hyperloop One and Hyperloop Transportation, another LA-based startup, are competing to realize Elon Musk's dream of super-fast transportation.
Now you've seen this thing many times, but we're going to take a much closer look at it today. What this is an air turbine starter for a jet engine. this jet engine. And there we go, our starter's attached, the airline is hooked up, the start cart's in position, and Mr. Bill is warming up the fuel system so we get a little bit of light rain just before we run this engine.
The first law of thermodynamics. It states that the change of the internal energy of a closed system is equal to the amount of heat supplied to the system minus the amount of work done by the system on its surroundings. An equivalent statement is that perpetual motion machines of the first kind are impossible. Second law of thermodynamics. Its first formulation is credited to the French scientist Carnot, who in 1824 showed that there is an upper limit to the efficiency of conversion of heat to work in a heat engine. Corollaries. Perpetual motion of the second kind. Before the establishment of the second law, many people who were interested in inventing a perpetual motion machine had tried to circumvent the restrictions of first law of thermodynamics by extracting the massive internal energy of the environment as the power of the machine. Such a machine is called a perpetual motion machine of the second kind. The second law declared the impossibility of such machines. I have recently been covering how water is fuel. I am in the process of making an electrical generator that runs off of water, converted to HHO. During my research, I have discovered that perpetual motion machines are not impossible. And thanks to David of Enslaved by Media, we now have confirmation of this.